ensemble methods first, and if we have time, then we'll talk about something next. Okay. Okay, so far what we have done is we have looked at different models that one can build, either for classification or for regression or even for clustering. And of course, for these models, we looked at different techniques or different methods for building those models. All right. So now one may ask a question, is it possible to combine multiple models into a single model? So ensemble methods do that. That is, you train multiple classifiers or multiple regression units or multiple clustering units, and then somehow or other you try to combine their results into one final result that is the result of your system. All right. So basically, we are trying to train multiple learners, and there are a couple of other names that go for these ensemble methods. You can also look at them as a committee-based method, because you have a committee of 5 people. Everybody looks at whatever is the case and gives their opinion. And by simple voting, one can assume one way or the other. Or if the committee members, some of them are more senior or carry more weight, then whatever they say is accepted by everybody else. All right. So, but anyway, that's a committee-based method. Or you can also call them as multiple classifier systems. So the basic idea is that you have the same input that goes into number of units or number of learners or number of trained models. And then the output from those different models is combined through some mechanism to yield a final output. Now, when we talk about multiple classifier systems or ensemble methods, we obviously have a number of different units that are participating in it. So question is, what do we mean by a homogeneous versus a heterogeneous ensemble? All right. So in a homogeneous ensemble, all the learners, which we generally call them as base learners, all the base learners are of the same type. For example, you might have trained 10 different decision tree models. All right, so there are 10 different decision trees that you have built using the data. So they are all the same type. All right, or you might have some of them as trees, some of them as naive Bayesian, some of the models following some other approach. Say, for example, multiple layer perceptron. All right. So if you have different types of base learners, then you say we have a heterogeneous ensemble. And if all the base learners are similar, following the same philosophy, same design methodology, then you say, all right, we have homogeneous. Now, these base learners that we use in ensemble methods are not needed to be very good. As long as they can perform, for example, classification slightly better than 50%, if you're talking of a binary classification, that's good enough. You don't try to design a classifier that will give you 80, 90% accuracy. You are just happy with 55, 58% accuracy in an ensemble method for each base learner. All right. So these base learners are thus known as weak learners. That is, they are not really good. They're C type of students. They are not A grade students. All right. So they are weak students or weak learners. However, when you put them together, they do a good job. All right. Now, Some of you might have read this story about a farmer dying and he's getting all his sons to his bed and he gives them a very thin stick to each one of them and asks them, can you break it? And very easily they all break it. All right. But then he says, all right, let me put all these sticks together. Can you now break this bundle? They cannot. All right. That's exactly the same idea. That is, you have weak learners. Each one of them by itself is not good enough, is of no use. But you put them together, they can do a really great job. Okay, so that's the basic idea behind ensemble method. All right. There is another name that goes for this, and that is called crowd wisdom or wisdom of crowd. All right. In a democracy, everybody is voting. None of us are qualified to talk about different issues in a very serious fashion, but put together, hopefully we end up with a decent result. All right. So again, that's the same idea of ensemble method. You're voting and then you do something on those votes and get a final result. All right, so let's see mathematically how is this possible. So suppose we have 5 completely independent learners. And let us say that each one of them has an accuracy of 70%. We combine these learners or their decision rule, and let's say we're talking of binary classification problem, all right? And so we have 5 learners, that means we get 5 votes, yes or no, all right? And we combine them using a simple majority, all right? If there are 3 yeses, then it is yes, otherwise it is no, all right? So what we can do is, we can figure out, given each learner is voting with a 70% accuracy, if we were to follow the majority rule, what will be the resulting accuracy? So in this case, of course, what you can do is, since there are 5 learners and we are talking of binary classification, so the total number of possibilities is 2 to the power 5 or 32, all right? So one can take those 32 possibilities and figure out in how many times we have 3 ones, 4 ones, 5 ones, and so on, and what will be the resulting vote, all right? And we know the probability for getting a 1 is 0.7 because we are saying 70% accuracy, all right? So based on that, one can do the calculations as I have shown you here. So you find that if you take 5 learners, each one of them 70% accurate, put them together, the result is going to be 83.7% majority vote. That means the accuracy you will get with these 5 learners is going to be 83.7, which is considerably higher than the 70%. All right. If you could increase the number of learners, for example, suppose you have 101 such learners put together, in that case, the accuracy you will get will be 99.9%. All right. So the point here is that although each learner is not very good at its job, but when you put them together, you can get really very good results. All right. The formula below is basically gives you the formula for binomial distribution, and with that you can actually calculate these probabilities. All right. So question is, all right, so it's good to have to know that, yes, we can do that. So question is, what are the requirements or how do we train these weak learners? And what are the characteristics that we expect or we should keep it in mind while building such a collection of weak learners? All right. So number 1 is these learners must not be strongly correlated. Rather, they should complement each other. Obviously, if 5 people are highly correlated, then there is not much independence in their works. All right. So when you combine them, it's not going to make a big difference. But if 5 people are thinking independently, arriving at their conclusions through their own thinking, which is totally independent from rest of the thinking, then when you combine them, chances are you will end up with a better result. All right. So we need to make sure that these learners are not strongly correlated. Okay, so that's number 1 point we need to do. All right. With that in mind, let's see what are the different possible approaches one can have, because we need to make sure that these learners are independent or not highly correlated. All right. That means one can go for different training algorithm. That is, these base learners could be different. One could be naive Bayesian, another could be decision tree, third could be Fisher's discriminant function, and so on and so forth. All right. Or what we can do is we can have the same algorithm, but different parameters, so that they are, not that much correlated.
Is this the homogeneous and heterogeneous?
Pardon?
Is this the homogeneous and heterogeneous?
Well, the first one will give you heterogeneous, all right? But in practice, I'm coming to different points, all right? Or you don't want to have different base learners, but you want to have same type of base learner, all right? But in that case, we have seen that different models require different parameters. For example, let's say that you want to build 5 neural networks. Then in each case, you can have the architecture different. You could start them with a different initialization, different learning rates. So you can make those parameters different so that there is, minimal correlation between those things. All right. Or what you could do is you could say, well, we will make sure that each learner looks only at a subset of features. It does not look at all the information. In that case, again, everybody is reaching their decision in an independent fashion. All right. Or we could even go to the extent of different data subsets for different learners. All right. So there are different ways of making sure that these learners have minimal correlation. All right. So the first one, if you have different algorithms, basically it will be heterogeneous ensemble. All right. The rest of the 3 cases are basically homogeneous ensembles. And again, within homogeneous, the number 3 point different features for different learners. That's the approach that is used for a random forest. And basically the final one, different data subsets for different learners, it's called bagging and boosting. All right. So again, one can have different ways of thinking. So let's look at what we mean by bagging. Bagging is an abbreviation of bootstrap aggregating. And the term was suggested and the method was proposed by Breman in 1996. Breman is pretty well-known person in the area of, we don't call it machine learning, he's with the Department of Statistics. But basically what they do is what we call nowadays as machine learning, okay? So basically, what is a bootstrap aggregating or what is bagging? Basically, in bootstrap sampling, what we do is we generate different data subsets for training different learners. So basically, you have a large collection of your training data. And what you will do is through this kind of sampling method, you will generate several data subsets for training different learners. All right. And then the output of different learners will be combined. All right. And bootstrap sampling involves sampling with a replacement. What that means is that you have a collection of data points. You pick a sample. Let's say you have 100 points and you want to get a sample of 10 points, let us say. Then you pick at random 10 points from that group. So those 10 points define your one subset. After you have done that, you put those points back and then again do the sampling. That's why it's called sampling with replacement. That is, you put these points back, okay? What does that do? That means if you are putting those points back, there is a chance that they will get picked again. So there might be data points in different subsets that might be common, all right? So if you look at this example that is shown here, you can see that we have, let us say, 4 data. We have a collection of data points, red, green, yellow, and blue, all right, on the left-hand side. And we are creating several bootstrap samples of same size, let us say, all right? So what we do is, first time we go and pick 4 points or 4 training samples at random, all right? So maybe we will pick red, green, red, blue this time, all right? And of course, these are put back. So we then next time when we go, it's possible we might pick yellow, blue, blue, yellow. Next time we might pick green, red, yellow, blue, all right? So the point is that there is a possibility that some of the data points will be picked up again, all right? And it has been shown that the properties of these subsets that you are sampling are very close to the properties of the original data set. That means if you build a classifier or a model using these subsets, that model is likely to behave as if it was built using the original data. All right. So here is an example of bootstrap sampling using sklearn. You can use sklearn to do that. All right. So in the sklearn utilities, there is an object called resample. There is a class called resample. So you can use that. And suppose the original data consists of 1, 2, 5, 7, 9, 13, 15, and 19. So these are just integer numbers. And we perform bootstrap sampling on this. And we want to get a sample size of 5, all right? And we specify some random state to initialize the process, all right? So in this case, if we do the bootstrap sample and we collect a sample of size 5, the examples or the numbers that are picked are 2, 19, 1, 7, and 2. So you can see that the number 2 has been picked twice. That is a property of bootstrap sampling. All right. So given M training examples, the probability that the ith example is selected k times is approximated by Poisson distribution with lambda equal to 1. Okay. We're not going to derive that. You have to assume that that's a correct statement or correct. All right. So basically, there is an expression for Poisson distribution shown there, and that basically tells you what is the probability that the ith example will be selected k times. Okay. Now, if you look at this expression, and from that expression, then you can calculate the probability that the ith example will occur at least once is given by 1 minus 1 upon E. That is on the right-hand side of the Poisson distribution formula. If you put k equal to 1 and lambda is equal to 1, you will end up with this number, which is 0.632. What it means is that each base learner uses only about 63% of the original training examples. So every base learner is looking at about 63% of the original examples. All right. Now, if you think in terms of what we mentioned right in the beginning of dividing your training set into, dividing your data into training set and test set using about 70-30 kind of thing. So something similar is going on here, that is each sample that you are creating has only about 63% of the data, rest of, all right. So what one can do is one can get an idea of the accuracy or the performance of the resulting systems by looking at what will be the performance on the samples that are not part, on the examples that are not part of a given sample. All right. So that performance is known as the out of bag performance or out of bag estimate. All right. Now, we mentioned weak learners, but we did not specify what is it, what kind of learners you really want. All right. So if you look at some of the models that we have discussed, let's look at the KNN, K nearest neighbor classifier. All right. Think of, you have a K nearest neighbor classifier. Even if you remove few examples from the training set, the performance of the K nearest neighbor classifier isn't going to change much. All right. Because it is looking at all the examples, trying to find out the closures and things like that. That means KNN is not very sensitive to few training examples being added or removed. So it is a very stable classifier. It is not a weak classifier. It is not susceptible to some small changes in your training set. All right. On the other hand, if you think of a decision tree classifier, while discussing those classifiers, I did mention that these are classifiers that are very susceptible to noise, some minor changes, and you can end up with a different tree structure. All right. Same thing, if you remove certain examples, you might end up with a quite different tree structure. All right. That means decision trees are what we call as examples of weak learners. KNN classifiers are examples of strong learners, or known as the stable learners. All right. And other classes fall somewhere in between. All right. So basically, if you want to use bagging approach, it turns out that you are going to get good results if you use unstable learners like tree learners, because then different samples of the data will create different trees which have very little correlation, and you will end up with a pretty good result. All right. So that's really what goes on. So here is just an illustration of what happens with this kind of approach. So what this slide is showing is results using simulated data. So the size of the sample is 30. So each tree is built using 30 examples. All right. And the data has 2 classes and 5 features. And this is simulated data. So each feature is having a Gaussian distribution, and the pairwise correlation is 0.95. All right, all that is. And then Y, which is the class level, is generated according to some formula. All right. So in any case, you generate a lot of data, and then you take different samples of size 30 each, and then try to build a tree. All right. So those are the trees that have been built. All right. Now, it turns out that if you're doing this kind of thing, you don't need to do any pruning. Remember when we talked about decision trees, I mentioned pruning is required if you basically grow a very big tree, because it kind of is doing overfitting there and things like that. All right. So in this case, we don't really need much pruning here, or no pruning, because without pruning, the trees are more unstable. As you make pruning, you are making the tree a little more stable. So what you want is unstable or a really weak leaf. All right. So you don't do that. All right. So basically, if you look at the results here, and basically the y-axis is showing you the error on the test data, and the x-axis is showing you the number of bootstrap samples. All right. So in this case, if you look at the original tree, that is, if you just took the entire data and built a single decision tree using the approach we had discussed earlier, you will end up with an error rate close to about 0.45. But if you use bagging and build number of trees, all right, you will end up with an error rate that is somewhere around 36–37%. And it fluctuates a little bit depending upon how many samples you have in your bootstrap sample. All right. That means you are able to get pretty good improvement using this approach. All right. So let's take a look at another example using this approach. So there is a diabetes data set. I don't know whether we have, I think I did mention that when we talked about decision tree, or maybe not. But anyway, there is a diabetes data set that's part of the sklearn library. So what you can do is you can basically use that data set to, to get some examples or to get some idea of how different approaches work. All right. So let's say that we use that data set. And first we build a decision tree classifier, simple single classifier. And we specify the maximum depth of this classifier to be 3. All right. And then we divide the data into train and test set, etc. And what we get is an accuracy of about 58%. All right. So if we were to follow standard decision tree approach on this data set, we will get about 58% accuracy on the test data set. All right. Now, at the bottom, if you look at the piece of code, what we are doing is we are basically trying different numbers of estimators, 10, 20, 30. So we are building 10 learners, 20 learners, 30 learners, all decision tree learners using the idea of bagging. All right. So basically we take the data and then we perform the bagging, create data sets, and then we build these trees. All right. So when I say I have 10 learners, that means I'm creating 10 samples using bagging from my original data set. All right. So if we do that, and for each case, if we look at the accuracy, you find that now we are getting 62, 68, 68, 67, 66, so on and so forth. So about 8 to 10% improvement is there by using this bagging. All right. So that basically tells you that by using ensemble methods, you can get improved or better performance. All right. So bagging is basically taking different subsets of the training data and doing the training. All right. A random forest has an extra trick involved. So you take subsets of data, but when you're building the tree, you look at subsets of features. So you do data subset and you don't look at all the features, you look at only some features. All right. So randomly you pick some features to look at and then build it. All right. So basically you're trying to improve the independentness between different trees that you will be building by working with different data sets or subsets, and also looking at not same set of features, but slightly different set of features. All right. So basic idea is shown here. So you start with all the data and you basically create random subsets of this data through sampling. All right. And then when you are building the tree from each subset, or for that tree, whatever random subset you have, you select a subset of features. So you don't use all the features. All right. So that way you will end up with much more variability in your weak learners or in your base learners. All right. So let's look at the same example, which is the diabetes data set. So we do that. And in this case, now we build a random forest classifier. And we say, all right, let's use 50 estimators. So in that case, the score on the training set is 100%. That's no surprise. And on the test set is 67%, which is similar to what we had gotten previously. All right. In this case, you can see that random forest is not giving you too much difference from the result that you get with bagging. But again, this is a small data set. So if you have much larger data set with many more features, it's quite likely that random forest will give you slightly much better performance. All right. So that was using what we call as bagging. All right. There is another method which we call as boosting. So boosting refers to any procedure that combines many weak learners to yield a much higher performance. The difference is that in bagging, all the learners are running in parallel, in the sense that you can train them in parallel. All right. There is no relationship, no constant that you have to train one learner first and then train another learner. All right. You want to design 10 trees, you can design them in parallel. All right. In boosting, the base learners are built in a sequential fashion. The basic idea is very simple. You build your first classifier for first weak learner. Obviously, this weak learner will correctly classify some examples, and it's going to make mistakes on many other examples. All right. So the next classifier that you want to build, you want that classifier to focus on examples that were incorrectly classified by the previous. So it's like when you're learning, I give you a simple exercise first. And once you are done with that, then I give you slightly more complicated exercise. And then I give you more complicated exercise and so on. The same idea, your first learner looks at the data and picks out the examples that it can easily solve or easily do. Then the next learner is told to focus on the examples that were not dealt with by the first learner. So next learner will obviously take care of some of the examples, but maybe still there are examples that are left that are not correctly classified. So the next learner will be told to focus more on those. That means successive learners are focusing on examples that were found difficult by prior learners. So it's a sequential approach. And obviously, it cannot be implemented in parallel. It has to be implemented in a sequential fashion. All right. So how do we ensure that the successive learners will focus more on examples that are difficult? That is done by using the idea of a weight. So you can say that every example is assigned a weight. To start with, every example has the same weight. And this weight, you can say, is a probability that that example will be picked up by the learner for training. So the examples that we want the learner to focus on obviously should have higher weight. So what is done is initially every example has the same weight. And then after the first learner, the examples that are getting misclassified, their weights are bumped up so that they have a much higher probability of getting picked up for training. Or you can also look at it in this way that when the weights are picked up and increased, so whatever cost function you have, the cost of misclassifying those examples is much more than the cost of misclassifying the easier example. All right. So the idea of weight is kind of tied with the cost or the loss. All right. And since we are building these classifiers in sequence, so once we are done building all the classifiers, what we can do is we can tap the output of each classifier and then use that output to come up with a final result. So here is the basic algorithm for boosting. Essentially, it's just one journal loop. So set all examples to have equal uniform weights. And then from small t, for t from 1 to capital T, where capital T is the number of classifiers or the learners that you're building, learn a hypothesis, that is build a model, h of t from the weighted examples, decrease the weights of the examples that are correctly classified, or you can say leave their weights unchanged and increase the weights of examples that are misclassified. Either way it works. All right. So basically that's the idea of boosting. And very first algorithm for boosting that became very popular is known as the AdaBoost algorithm. And here is a pseudo code for AdaBoost, which is pretty similar to what I just explained in the previous slides. All right. And what we'll do is, obviously, when you have this loop, you want to put in some termination criterion so that the loop is stopped. So basically, the difference from the previous slides is that we have an error threshold, which is basically telling us when to stop and things like that. You can increase the weights in two ways. One is, if an example needs to have a weight which is 5 times the basic weight, what you can do is you can replicate that example 5 times. Obviously, then the probability that example will be picked up has gone up 5 times. All right, so that's one way of doing it. Or you can basically modify the formula for your cost function, where you basically include the weight of an example in the cost function, and that is where you keep track of the weights. Okay, so both ways people work. It's up to you how you want to do it. So here is a visual illustration of what we call a boost example. So on the top corner, on the left-hand side, you have basically a set of examples from two classes, points being designated as plus and minus, so positive class and negative class, all right? At the bottom row is the result of your first week classifier, all right? In this case, the classifier is a simple decision tree classifier just with one test, all right? So the test is, in this case, whether, wherever you're placing that line, that is indicating the test that is being done by the tree, all right? So if I place the line there, that means if I compare the X coordinate value or X value or the horizontal value of the attribute, and if it is less than or it is to the left of the line, I say it is a positive example, all right? So you can see that two positive examples are correctly classified. All the negative examples are correctly classified because they're on the other side of the line, but there are three positive examples that are misclassified, all right? So let's go to the top row now in the center panel. So if you look at the top row in the center panel, you will find that the size of the plus marks or cross marks for the examples that were misclassified, that size has gone up. The examples that were correctly classified, positive or negative, their size has gone down. That means what we have done is we have modified the weights. We have increased the weights for the plus misclassified examples. And for rest of the examples, either we have kept the weight same or we have decreased them, all right? So now if we work and try to find a new classifier at this stage, so that result is shown in the second row in the center panel. So basically we find that if we place a line towards the right end, that line is going to be our next learner. And with that, we can see that it correctly classifies two negative examples. It correctly classifies all the positive examples, but there are three negative examples that are still being misclassified, all right? So that's why if you go back to the top row, now you find that those three misclassified negative examples, their size has gone up. That means their weight has gone up, all right? And now if we build a classifier at this stage, basically the result is what is shown at the bottom diagram, all right? So now we find that with that, everything is getting correctly classified, all right? So what we can do is once we have this, we can combine these different classifiers to yield a single classifier, all right? And at the bottom, we are keeping track of what is the accuracy and all that. So basically, when we combine these classifiers, we can weigh them based on their performance, give them importance according to how well they have done, all right? So if you do that, we can, combine them. And after that, you see at the bottom, the final classifier that you're getting, all right? So this is what this approach does. That is, you build these classifiers sequentially, focusing on examples that were not dealt nicely with the prior model or prior learner, all right? So that's basically the approach that is followed. And as we saw in this particular example, and I mentioned, one can combine these weak learners by a number of ways. The example I showed you was for classification, all right? If you were doing it for regression, you can simply do the average or weighted average of output from different learners. For classification, you can do simple voting or weighted voting for different learners. Sometimes people like to do what we call as stacking. That is, treat each learner as producing an output feature. So basically, take the outputs of different learners and then try to adjust the weights between those different learners and the final output unit, which is combining them through some training scheme. All right. And that is what we call as stack learning, or combining them through stack. All right. Any question?
General question. So basically, KNN means you will never use only decision trees.
KNN is not good for boosting or bagging because it's a very stable classifier. Even if you pull out some examples, the performance difference is not going to be much. So essentially what is used in ensemble methods is more or less decision trees. All right, because those are brittle, those are sensitive to noise, so they are suitable for this task. All right.
Bagging and boosting can be combined.
Pardon?
Bagging and boosting can be
Well, yeah, certainly you can, again, if you want, you can possibly combine them, but I haven't seen people combining them. But you may not get much advantage by combining, because if you're already, reaching 88% from one unit, the other one might give you 88.9%. So when you combine, you're not going to get. See, when we are combining these weak learners, we're getting a boost in the performance because each one of them is not really doing that great. But if you already have a unit that is doing very great, there is not a whole lot you can do with that to, improve its performance further. So it's possible, but it may not give you much improvement.
When you talk about this stacking,
Stacking.
can you identify the features on its own?
Well, basically, just think of a perceptron network. All right. What is in the perceptron network we are doing? We have n inputs. And basically, we have a training examples with n inputs, and we are saying whether we want 1 or 0. And through those examples, we basically train the perceptron. All right. Similar thing here, you have n weak learners. So you have the output of these weak learners. So you have, let's say, 10 weak learners. So you have 10 outputs. And then you have a final unit, which is supposed to produce 1 or 0. And these 10 outputs are 1 or 0s. So basically, you are getting these results from 10 classifiers or 10 units, and you want to combine them into a single result through training. So basically, the problem becomes the same as what we have done so far. All right, so let's talk now of what we call as gradient boosted. These are much more powerful than what we have discussed so far. All right. So gradient boosting is another way of building a sequence of weak learners, in particular a sequence of trees whose outputs are added to obtain the final prediction. The sequence of trees that we build in this method are essentially trees, which you can call them as stumps, or trees with depth of 2. That is, you build very small trees. You don't build big trees. All right. So trees with, 2 terminal nodes, or at the most 4 terminal nodes. All right. So that's what we do. In this method, there is no concept of, although you are building in a sequence different trees, but we don't use the idea of giving weights to examples that were misclassified or things like that. Instead, the idea is to minimize some kind of loss function as we build successive trees. All right. So here are the steps for building an ensemble of gradient boosted trees. And these steps I will show you through example for regression as well as for classification. All right. So step one is to construct a base tree with a single root node. That is just a tree with just one node. All right. And that tree represents the initial guess for all the samples. All right. Suppose I want you to guess the weight of one of the students in this class. All right. All you have is the weights of every student. All right. So you have the names and you have their weights. All right. At some point, I hide the names. And I say, all right, what is the weight of student number 6 in my randomized list? All right. What will you do? Everybody understand my question, or you want me to rephrase it?
If you just suggest
Hmm?
any random number.
Well, certainly you can give as a guess any random number, but that's not a good way of solving problems.
Can we consider the range as well?
No. Let me put it. There are 10 items with their weights ranging, let us say, from 10 kilograms to 100 kilograms. All right. These 10 items have different weights. All right. Then and you have looked at those items. All right. And you looked at, okay, these are the 10 items, these are their weights. All right. And then I send you outside the room. You cannot see them. And I say, all right, I'm holding one item in my hand, or I'm tapping on one item. Can you guess what is the weight of this item?
Average.
The only recourse you have in that case is to come up with an average, because if you're trying to minimize the loss between what you're guessing and what is the actual weight, in absence of anything else, average is the one that will minimize the loss, mean square error with respect to average. All right. So that is what will be the answer. So the first root node is simply generating an answer without looking at any features and saying, okay, the output of my regression unit is the average of whatever data I have. All right. So once you have that, you can now compare that average with respect to the actual values. And that will give you the difference between what you guessed and what is the actual number. All right. So that is what we call as residual. So in step 2, what you do is you look at these residuals, or you look at these error values, and now try to build a regression tree looking at features so that you can make a good prediction for these errors. Okay. And again, the tree that you want to build is not going to be a big tree. You don't want to solve the problem at this stage. You want to just build a very small tree with either 2 nodes or 4 nodes. All right. So you build another tree, and that tree, again, in most problems, most applications, will give you some improvement in your result, but it will not give you the ultimate result that you want. All right. So basically what you can do is you can follow this step again. So you can say, all right, so far through these steps, this is my guess. This is the actual numbers. So that's the difference at this stage. Can I again build another tree and minimize this? So basically what you are doing is you are guessing, you are checking how much is the error in your guess, then you are making a new prediction, which you add to your old prediction. And then again, check for the error, make another prediction, add to the old prediction and all that. And while you're doing this, you're basically minimizing the mean square error. And this process of specifying how you are adding and all that basically turns out that if you write down the formulas for mean square error and for updating, basically you are taking the gradient and all that kind of stuff. So that's why these are called gradient boosted trees. All right. So basically, those are the steps which are very similar. So let's look at an example that gives you a good idea of what's going on. So here is a regression problem. So basically, we have same problem that I mentioned, the weight, but in this case, we are looking at height of a person, age of a person, and gender. So those are the three features. And we have, for each example, the corresponding weight value. All right. So what we want to do is we want to build a regression model where if we give the three features, height, age, and gender, the model will predict what is the weight of the person. All right. So that is what we will do. All right. So as I said, if you don't look at any feature, if I hide the first three columns, the only thing you can say about any particular person in this is you can come up with an average value. All right. You can say that is the answer I'm going to give. So basically in this case, the average is 71.2 if you were to take it. All right. So that's your guess, starting guess. All right. And since you are not using any features, so you can say that this guess can be represented as a single node with a value of 71.2. All right. So what you can do next is you can say, all right, I know the actual weights and I know what we predicted in the previous slide or previous step. So I can take the difference between the two, and that is what I can call as the residuals at this state or pseudo residuals at this state. All right. So if we do that, we end up with these numbers 16.8, 4.8, and so on and so forth. All right. So what I can do now is I can take the first three columns as my input features and the pseudo residual column as my target variable and generate a regression tree. And again, I don't want to generate a huge tree. I limit my regression tree just to 4 terminal nodes or to the depth of 2. All right. So basically you can say, all right, if I build a tree and first root node, I check whether the person is male or female. So if it is male, we go on the left-hand side or right-hand side, depending upon where is yes and no. And then we check for the height on one side and check for the age. All right. So basically, if we build a tree like that, we will end up with 4 terminal nodes. And these examples will then filter down to these terminal nodes. So you can see that for the first terminal node to the left, there are 2 examples that are filtering down. And those 2 examples correspond to pseudo residuals of 1.8 and 5.8. All right. And similarly, you can see how the rest of the examples are filtering down. All right. Now, in decision trees, regression trees, whatever you are doing, the terminal node should have a single value. It cannot have multiple values. All right. So in this case, for the leftmost terminal node, we got two values or two examples that are going down there. So what we will do is we will take the average of those two residuals and say that is the prediction that is associated with that terminal node. And we do the same thing for rest of the terminal nodes. So if you look at the right-hand side tree, everything is same except at the terminal nodes, we have the average values coming from the terminal nodes of the left-hand side. All right. So basically, that is our new prediction or prediction for the residuals, not prediction for the actual weight. All right. So what we will do is we will add this prediction to our earlier prediction. And this addition is done using a factor or a constant that you call as a learning rate, because that comes from, again, the same idea of gradient approach. All right. So in this case, the learning rate, let us say, is 0.1. Typically, it will be in the range of 0 to 1. All right. So let's say it is 0.1. So what we can do is we can use this learning rate and all the previous predictions to basically do the updated prediction at this stage. So that is shown as predicted weight number 2. All right. That is the fifth column in the table. All right. So that's the prediction we are able to make at this stage. All right. Again, what we can do is we can compare this with the original predictions or with the original values and see what is the amount of residual still left. All right. So the final column is telling us the residual at this stage. Okay. So again, what we can do is we can take the first three columns as the features and the final column as the target output and build a new regression tree, again, limiting it to only 4 terminal nodes. All right. So that new regression tree is shown here. And again, some of the terminal nodes will have more than one example falling there. So you take the average there. And then basically, if you look at the tree on the right-hand side, that is the tree that is giving you prediction at this stage for the residue. All right. So what you can do is you can repeat the process and generate new set of residuals and repeat the process again. And you can keep doing this till you come to a stage where the difference between your prediction and the actual value, the mean square error that you have, is at a level that is acceptable to you. And at that stage, you can say, all right, I got my collection of trees that are part of my gradient boosted regression. All right. So that's how this process works. All right. Any question? All right. So that was for the regression. Now, what happens if you were to build a tree for classification? All right. So for classification, as you can see that what we were doing is we were taking the residuals and all that. And obviously, if you're going to work with classification, the residual idea is not going to fly directly. So what is done is that we convert the qualitative output to a quantitative output. That is, for classification, the output is supposed to be positive, negative, yes, no, A or B or whatever it is. All right. What we need to do is we need to convert this output to some kind of numeric output, quantitative output. And once we are able to do that, then we can apply exactly the same approach that we just went through. All right. So that is done using the idea of log odds that we discussed while talking of logistic regression. You remember, we talked about regression and then we talked about logistic regression. And the difference was that logistic regression was designed to predict, to do classification, all right? The approach was still based on, finding the coefficients of a model, a linear expression, and of course, we were using a sigmoidal function there instead of using the linear expression directly. And that's where we defined the log odds and all that. So basically, the classification problem is handled using the idea of log odds that comes from the idea of logistic regression. All right. And I have given you the link here. So let's see if we can just browse through that. Okay, I think people are going to be saying, all right. Okay. Are you guys still able to see, or I need to?
Yeah.
Huh? So the screen is changed now. Huh? Okay.
It's not yet.
Okay, so let's go back and we will. Okay, so where is the new one? Okay, we got it. Okay, so now we will just go over there, and I highly recommend that you go and take read this post. Okay, it basically, I'm going to browse over it. Okay, so just defines what is boosting and all that we have done at a boost. All right, and here is a walkthrough example to build a gradient boosted regression tree. This is done using a much simpler example with 2 features. All right, so you can go through it, but the process is what I just now explained. So basically, in this case, there are 2 features that are basically inputs to a field, fertilizer input and insecticide input amount, and the column Y is the amount of crop yield that you are getting. All right, so you're trying to relate 2 inputs to the output. All right, so that's a regression problem, and basically we just went through a similar example, and that's really what is shown here. All right. And the beauty is that actually you can do this example step by step using sklearn library with a simple decision tree regression. You don't need any gradient boosted and all that. Step by step you can do it, and you will understand very well then how it is done. Okay, so that is what is shown here. So you got the residuals again after that, and then you build new tree, new residuals and all that. All right. And here is basically, you can also get the same result using gradient boosted regression from sklearn library. So either way you can do it, you will find that you end up with the identical result. So basically that tells you how this is being done. All right. So now let's come to the classification. So let's take the same problem, but we just modify it. And instead of the target variable being the crop yield, we just converted it into 0 and 1, indicating that crop was good or crop was bad. All right. So basically it becomes now a classification problem. All right. So if we want to solve this, the first step is identical to the step that we follow in the gradient boosted regression tree. That is, we take the target variable, take the average, and say that is our first prediction. All right. So in this case, if you do the average over ones and zeros that you have, your prediction is 0.667. All right. That really doesn't tell you in terms of the class label. So that is where the idea of odds ratio comes in. Now, I'm sure you have seen this formula, yi times log p plus 1 minus yi times log 1 minus p. All right. Basically, this is defining the negative log likelihood of a loss for the ith training example, where P stands for the probability that the example is from class 1. All right. So basically, you can look at that, or you can go to the log odds ratio, that formula that we used when we talked about logistic regression. So P is given as e to the power log odds divided by 1 plus e to the power log odds. And through some simple algebraic manipulation, you can actually go through some of these steps and finally come to the second formula shown here, which basically tells you the gradient information. You can see that you're taking the derivative on the left-hand side with respect to log odds. So basically, you do the gradient with respect to log odds, and everything works out well. So that's basically what is done in case of decision trees. So basically, if you follow this blog post, you will go through step by step how this approach works in the case of classification problem. All right, it's done in a similar fashion, step by step, except that instead of taking the target output, we are now taking the log odds as the output and trying to fit our trees to do that prediction. And that turns out to be way of predicting your class labels. All right, so please go over this. And here is the same thing with sklearn library you can do. Now, there is another method which is even more powerful than gradient boosted decision trees. This is called XGBoost or extreme gradient boosted. All right. The main difference between the extreme gradient boosted and what we have discussed so far is how the implementation is done. That is, extreme gradient boosted uses number of, because some of the examples we are showing you are examples for very simple cases. All right. But think of doing these things with millions of examples and things like that. So you need the methods that can scale very well. All right. So XGBoost has certain built-in tricks that gives you a faster implementation as well as a slightly improved version of gradient boosted tree. In some simple sense, you can say that XGBoost is a scaled version of gradient boosted tree. All right. So if you want to read about it, there is a link there. You can actually check that. And as per most of the reportings, for any numeric problem, the kind of problems we have been working with, XGBoost seems to give the best performance. So if you were to use only one method and somebody told you that's all you can use on one method, my suggestion will be to go for XGBoost, because that's basically gives you the best. All right. So with that, I think we will stop with discussion on ensemble methods. I didn't mention anything about clustering, all right? But it's possible to do clustering also using ensemble methods. And the places where you use clustering with this approach, let me explain where you would like to use. Typically, you are using k-means clustering. In k-means clustering, you are looking at distances between the examples or the distance of an example from a center. As long as you're working in a dimensional space of 10, 20, 30, it's okay. But if you are working in a much higher dimensional space, you will find that the distances between different points do not vary much because of the dimensionality of the space. That means if the distances are not going to vary much, you're not going to be able to make use of k-means. So typically what is done there is you take your feature vectors and you divide your feature vectors into sub-feature vectors. Say, for example, you have a 100-dimensional feature vector. Maybe you can divide that 100-dimensional feature vector into 10 sub-feature vectors, each of 10 dimensions. And on each of them, then you can perform the k-means clustering. So you have now 10 k-means clustering results coming from 10 different units. Then you need to combine those results into a single result. And again, to do that, you take the idea of rand index, etc., that we discussed earlier. So through some of those tricks, you can actually combine them and get the final clustering result. So it's not that you cannot use ensemble method for clustering. They are used, but they are used mostly in cases where you really are working in a very high dimensional space. All right. So with that, we will basically close out this discussion.